Hello, my name is Lara Suarez Casabiel, a researcher from IMEN, and today I will present the Aeration optimization control for digital twin developed for the TRINEFLEX platform. Aeration is one of the most energy-intensive processes in wastewater treatment plants. Energy cost is a key factor in the aeration control. We also know that electricity prices may vary depending on the time and the season. The image shows the periods defined by the Spain government for a 6-period tariff. Each period has a different cost, where 6 is the cheapest one and 1 is the most expensive. Adjusting operational to lower cost periods helps reduce operational cost, and the tool allows the aeration to be adapted according to these tariff periods. Ammonium thresholds can be configured per period, and the objective is to shift or optimize aeration toward cheaper time slots whenever possible. The main objective of the tool is to test and validate different aeration control strategies in a safe environment. It was developed based on the SAMUR use case, incorporating improvements to reduce energy consumption, avoid unnecessary long aeration periods, and maintain biological process efficiently. Some of these new features include the nitrification control. The system evaluates whether nitrification is taking place based on sensor data. It detects process evolution using ammonium and radon trends and identifies the end of nitrification. Maximum nitrate threshold was included. If nitrate exceeds this value, the blower is stopped to prevent over-aeration and unnecessary energy use. Lastly, the tool also includes a 30-minute short-term prediction of process variables like ammonium, redox, and nitrate. The user can force the blower to turn on and off regardless of the simulation logic in the final steps of the simulation, and this is useful for testing specific scenarios and validating short-term predictions. Overall, the tool allows users to evaluate how different configurations impact system performance. Let's take a look at how the system works from end to end. The architecture is divided into 4 domains: physical, communication, digital, and user domains. In the physical domains, different sensors measure key variables such as ammonium, redox, oxygen, nitrate, and the blower status. The data is then transmitted through the communication domain to the digital twin platform called CARON. There, the data is stored and then used by the tool, together with the parameters defined by the user. Based on this information, the user interacts with the system through the user domain using the TRINEFLEX Decision Support System, or DSS, which provides a simple and intuitive interface. This slide represents the basic configuration interface available for the user. First, user selects which sensors are included in the simulation. This determines how input data is processed, if the control of the blower will depend on both of the biologicals or only one of them. Users can define thresholds values according to plant operation. Ammonium thresholds can be adjusted depending on the tariff periods. If ammonium exceeds a maximum value, aeration starts. If drops below the minimum value, aeration stops. And in the case of the threshold value, if it drops below it and the redox is stable, then aeration stops. If not, the aeration continues. This flexibility allows users to tailor the simulation to real plant conditions. In this short video, we will show how to configure the main simulation parameters to run a simulation in the DSS. Once the basic setup is complete, the ammonium thresholds can be defined, as these are the most relevant parameters. As we saw previously, the main control of switching on and off the blowers together with the redox slope, and additional parameters can also be selected and the simulation then can be run. Once the results are available, the tool provides a clear visualization of key process variables over time, including ammonium, redox, and nitrate levels. Aeration periods are highlighted in yellow when aeration is active. The platform also includes a prediction model that forecasts process behavior for the next 30 minutes. Its results are indicative and depend on both the simulation results and the real data parameters used. Therefore, they may vary between simulation, and the predicted variables should be interpreted as an indicator of the trend rather than a deterministic value. The performance of the prediction models are automatically checked every month to ensure they remain accurate as new data becomes available. Users can consult this, and they can compare also the prediction results under different configurations and the simulation results with historical data to evaluate them. So as we say, the Aeration Optimization Control Tool provides a safe environment for testing aeration strategies and combines real data simulation and long-term predictions. Thank you for your attention.